Hi folks, so we're going to be taking a look at the long-run behavior of polynomial functions as it says in the title, and we will be using the class notes and example sheet from sections 2.1 and 2.2 which says it's on polynomial functions. You should go to page 2 of that, and I think you'll see a heading that says the long-run behavior of a polynomial. So I want to give you a little bit of time to try this on your calculator. The idea is to graph two functions. So you'll plug one of them, you can plug f of x in as f1 of x, and you'll plug g of x, you can plug that in as f2 of x. And then you're going to graph it first on this window from -3 to 3 and -10 to 50. That would be -3 to 3 is the x's, and -10 to 50 would be the y's. You can access these controls by going to the menu button and then option 4, window zoom, option 1, window settings, and you should see ways that you can enter an x-min, an x-max, and then a y-min and a y-max, and that's what would be these numbers here. I might add that when you first try to graph it, before you've change your window, you might not see a graph, at least for f of x. It may not actually be in the normal standard window, but you should see g of x in there, and then when you change your window, you should see both graphs. So pause the video and give that a try. See if this is what you got. As we might expect, these two graphs look fairly different. You would think that, they're not going to look the same on this window, and indeed they do not. But let's take a look at these graphs a second time. This time you're going to be graphing them on the window where the x's go from -20 to +20. So you're going to be using larger values of x, and in order to do that, you're going to have a pretty big window for y. We don't need to go down in the window, but we're going to go all the way up to 100,000. So I would suggest that you open a new page, adding a page by hitting Control and Document, and then choosing a Graphs page. And if you scroll up in the menu where you enter your functions, you'll see that you still have this function in as f1 of x and this function is f2 of x, but you might need to turn those on by hitting Enter when you're in their boxes. And then you can go back and reset your window or set your window up to go from -20 to 20 for x's and -10 to 100,000 for the y's. All right, pause the video, give that a try. Thanks for doing that, and see if this is what you got. As you can readily see this time, rather than having two graphs that look quite different, we actually appear, it almost seems like we have the same graph. That is kind of interesting that when we open up the x values and start looking at larger x values, these two graphs appear to almost be the same function. Why is that? We can start to think about the fact that when we are raising numbers to the 4th power, that is really going to be a lot more dramatic than when we simply square them or just multiply them by 6. Okay, so you can almost think about the fact that this term, this x to the 4th term, kind of takes over when you start plugging in large values of x. And I might add that these aren't all that big of values. We're talking about -20 and +20. If we start plugging in numbers like 100 or 1,000 in for x, it really becomes even more dramatic that this graph, this blue graph, actually starts mimicking the red graph, the x to the 4th graph. So this is one reason we've been talking about the leading term of a polynomial. It plays a major role in how the graph is going to look when you start heading out towards +infinity, when your x's head towards +infinity, or when your x's head towards -infinity. We can pretty much kind of discard the other, or not pay attention to the other terms except for the leading term. That is what the graph is going to look like. I'm taking just a little closer look to this to kind of show you what's going on here. So we have a column here where I'm just having my inputs. These are going to be my x's. And then I have a column for my outputs of the first function, that f function, the polynomial. And then here's the outputs for g of x, which is the leading term, that x to the fourth term. Now, when you just subtract the the g of x values from the f of x values, that's what I'm doing here, you can see that certainly when x is equal to 2, they only differ by 52 units. And when x is equal to 10, our output values are differing by 580. And then when we're up to 20, it's differing by 2,000. So it seemed like a much greater difference when we have large values of x. However, if we take the f of x value here, 68, and divide it by the 16, we can see more of what's happening when we have large values of x. Okay, when we're just plugging in 2, which is a pretty small value for x, the output value for f is 4 times or more than 4 times greater than the output value for g. However, when we look at 10 and even 20, you can see that the ratio of output values is almost the same, right? We're close to 1. Our ratio is 1, which means our two values are very close to each other. And that's what's going on here. And of course, the further out we go, if x becomes 100 or 1,000, this ratio is going to get closer and closer to 1, which essentially means you have the same output values. All right, so let's just make a general observation here that as x is approaching plus or minus infinity, that means we could go either direction, right? We could be, if x is approaching negative infinity, then we are heading to the left, all right? And as x is approaching positive infinity, that means we're heading to the right. And in both cases, whether we're heading to the left or the right, we can see over here that f of x comes closer and closer to mimicking g of x, which equals x to the fourth, right? And that x to the fourth is the leading term of our polynomial, right? So essentially, as we were saying, the leading term takes over. All the other terms kind of don't matter as much because you're only squaring it. You're only multiplying your x's by 6, and that doesn't. And adding 20 is next to nothing when you're raising your large numbers like 10,000 to the fourth power. Okay, even 20 to the fourth power seems to be enough. So in general, what we have here is if we just have a general polynomial, we'll use p of x. All right, a lot of times we'll use p for a polynomial. So p of x, and this is just the general form written in standard, in the standard way. So generally, p of x, the long-run behavior of p of x is that p behaves in the same manner as the power function y equals a sub n times x to the n when x becomes really large, okay? And we can just say that what we're saying here is that the leading term takes over for large values of x. How about that? Large words for large values of x, okay? That's what you got to remember. So when we're talking about x heading out towards infinity, we can just ignore all these other terms and just pay attention to that leading term. Whatever that leading term is going to do, that's what the polynomial is going to do. So let's see if we can apply some of this to a problem that you might see. You probably won't see a problem like this on the immediate homework, but down the line, they're going to be asking you to maybe graph functions like this. Now, this is a polynomial. If we were to multiply these three terms out, we would get a bunch of power functions added, and then all their exponents would be whole numbers. But you'll notice this is written in factored form, which is a much more useful way of writing a polynomial so that we can graph it. Because what we can do first is just very easily determine the x-intercepts, or what we might call the zeros of the polynomial. All right, so if we set y equal to 0, right, we can determine what the x-intercepts are. And because we're in factored form, this actually makes it pretty easy, right? We just set each factor equal to 0. And when we do that, we'll end up with x equal to -5, or x equals -2, or x equals 4 from that last one. So we know that 3 points on our polynomial are -5, -2, and 4. All right. Now, polynomials, as I think you're aware of with square graphs and cubic graphs, are nice flowing curves. And so we have some choices here. You know, it's possible that our polynomial might come down and intersect, try to do this a little better, intersect the 5, and then come back up and intersect at -2, and then come back down, trying to draw a dash graph, come back down and intersect +4, and then just keep going down, right? That's one thing that could happen. Another thing that could happen is it could come up, right? Intersect the 5, the -5, come back down, intersect the -2, come back down, and then intersect the +4. Go like that. So the question is, which way does it go? It's one of those two ways, right? Well, there's a couple of ways we can tell which one it is, but one way that I'm pointing out for today is we can look at the long-run behavior. We can think about what would the highest degree term, or the leading term, be in this polynomial, right? And we can get that just by thinking about what would we have if we multiply the x times the x times the x. We know that this polynomial is basically going to look like y equals x cubed, okay? And that tells us whether we end up going up at the end, or whether we end up going down at the end, right? We just have to think about the power function y equals x cubed. And since we know y equals x cubed does this kind of thing, then that means it must be the green, right? We want to end up going up as x is heading towards infinity, okay? So let's go to the next slide. We'll draw it out properly and then look at the last little piece here. Well, I was hoping my pen wouldn't wiggle so much, but it's really hard to draw a straight curve here, so ignore the wiggles. But basically, yeah, this is what the graph should look like based on our analysis. Now, there's two more questions here to answer down at the bottom, as you can see. So as x approaches -infinity, y approaches blank. And so all this is asking, and let me go to maybe a different color. So as x approaches -infinity, that means as the graph moves to the left, right? Because -infinity is to the left. What are the y values doing? All right, so as the x's head to the left, you're just trying to ask, are the y values rising or falling? And in this case, they're falling, so we would say that y is approaching -infinity, okay? Because it's heading down, okay? And then let me switch over to green here, all right? As x is approaching +infinity, are the y values rising or falling? In this case, we can see they're rising, right? They're going up, and therefore we would say that y is approaching +infinity. So that's how you answer that. And remember, these two lines, all we had to do was pay attention to the leading term, right? Thinking about what the graph of y equals x cubed looks like, and that's what this curve's graph is going to look like. It's generally going to be going up as we head to the right and going down as we head to the left. I will just mention there is one more way we can know that the graph is going to do this as opposed to what we had set up before, where it would come down, go up, and then come back down. And that is by looking at the y-intercept. You know, earlier we let y be 0 and found the x-intercepts. If we let x be 0, plug this in here, we'll just end up with 5 times 2 times negative 4, which ends up being negative 40. All right, so when we plug 0 in for x, we get back negative 40 for y, and that can let us know that, oh, yeah, we do need to be down here for our y-intercept. In fact, we know this number actually has to be, go with a little thinner line here, that this number actually has to be negative 40. All right, anyway, that's just a little check on the work we were doing. So now it's your turn to, let's turn it around and see if you can sketch a graph that has these two properties, so that as x approaches negative infinity, y approaches positive infinity. And then as x approaches positive infinity, if you don't see a plus, it's just positive infinity, then y is also approaching positive infinity, right? There's different things that can happen. Pause your video and give that a try. See if this is what you got. Yes, essentially, if you drew something that just looked like a parabola or close to it, I've got those wiggles in there. Of course, you could have gotten a little fancier and just come down like this and done a couple of curves and then gone up. That would have been fine too. But all we care about is the end behavior. Are we rising as we're moving left, and are we rising as we're moving right? That's what this is describing. Okay. Try letter B, and pause your video now. All right, is this what you got? So we can see here that whether we're going left or right, we want our y values to head down, right? Go to negative infinity. So basically, it kind of looks like could be an inverted parabola if you wanted to do that. There's one more on the next page for you. Give this one a try. It's a little different from the other two. All right, see if this is what you got. So a little bit of an inverted. Now, one thing we haven't been talking about is whether the degrees on these polynomials would be even or odd. And it is something that we can tell from our graphs, right? This one would have to be odd, because this would be more like a cubic function that's got a negative coefficient on it, right? Normally a cubic would go up like that, but this time it's coming down. The other two that we had one going up, up on both ends, and another one going down on both ends. We know those have to be even degrees, because that's what like x squared, x to the fourth would do, or a negative x squared, negative x to the fourth. So on the homework that you might do for this section, just know that generally when you're trying to, let's say we had this polynomial, this is the one we were working with earlier. Let's say we had this polynomial and we wanted to match it to a graph or something. The main thing we would pay attention to would just be its leading term, and that would be this negative 1/2 x to the 8th, right? I think we identified that earlier. Well, whatever y equals negative 1/2 x to the 8th does, whatever that graph does, that's what f's graph is going to do. And I think we pointed out in the past that if we drew in some axes, that we know that it's got to be, doing the same kind of thing that x to the 8th, that negative x to the 8th would do. The 1/2 is just going to make it compress vertically, but we don't need to worry about that. We just think about what would the negative do on x to the 8th. And since it does that, we'll look for a graph that does that. Now maybe the actual graph has some other bumps along the way, does that kind of thing, but we know we should be looking down and down on both ends of the graph. All right, hopefully that helps with the few problems you're going to have on this in your textbook.